Hello, my name is Michail Georgiou, and I'm an architect associate professor at the Department of Architecture of the University of Nicosia in Cyprus. I'm the coordinator of the new Master of Science in Computational Design and Digital Fabrication, through which the research project presented today has been produced. This paper, titled XMAX, a digitally fabricated component-based scrap metal assembly, is co-authored by my colleagues Odysseas Georgiou, Pavlos Fereos, and Eftihis Efthimiou. The paper presents findings from a recently realized case study titled XMAX. The prototype was designed and constructed during an educational intensive 2-week workshop that focused in digitally fabricated 3D component-based non-Euclidean geometries using sheet metal forming. The research activity was part of the curriculum of the first semester of the distance learning MSc program in Computational Design and Digital Fabrication of the University of Nicosia, in collaboration with the Institute for Experimental Architecture, Hochbau of the University of Innsbruck. By comparing and grouping related case studies, differences and similarities with XMAX were asserted, both prior and after the project's completion. Precedents were categorized in those employing sheet metal forming, creating continuous surfaces similar to origami folds, and those presenting discrete components supported in most of the cases by a substructure. Based on the above analysis, the research team strived to explore design solutions that would not be initiated or result in a continuous skin structure, would prioritize material forming accuracy, and would be self-supported despite utilizing discrete components. In parallel, as no other project using scrap sheet metal has been encountered, this aspect of the research has been explicitly analyzed and presented. As such, the research brief prescribed a bottom-up design approach through which the participants were asked to define a component, its performance and connectivity to neighboring units before proceeding to compose and articulate surface structures exhibiting three-dimensionality, porosity, and transparency. Early design proposals were compared and evaluated based on the hypothesis that improvements in material efficiency and construction logistics can contribute towards more affordable design solutions. Following an evaluation, the fit test solution was further developed and optimized for construction, resulting in a full-scale prototype demonstrating proof of concept. The XMAX was generated by populating a single adaptable 3D component to form an efficient, self-supported, doubly curved structure. 190 components were developed into load-bearing modules that could be digitally fabricated out of flat sheets of material and then CNC bent in shape using variable bend angles. Modules were connected using bolts to form circular rings that could be vertically stacked and then secured using the self-weight of each row. The modules were made using galvanized and mild steel of various thicknesses and were arrayed forming an ascending pattern. The installation weighed 250 kilograms, its footprint ranged at 2.4 meters square and its height at 4 meters. All parts were assembled in a puzzle-like routine in 8 hours over a period of a day by a team of 10 students. The assembly time and manual effort were substantially lower compared to the construction of equivalent research prototypes preceding XMAX, while savings in material resources were recorded. Scrap steel in sheet form was chosen as construction material to investigate and support the research hypothesis. The material was documented with orthophotography, implementing a drone, followed by an automated cleanup of the image files using a denoising algorithm and Gaussian blur function. The treated images were then vector traced and numerically tagged utilizing tracing and sorting algorithms. As sheet metal forming produces large deformations that usually surpass design tolerances, the research team aimed at computationally simulating the material deformation to reach the exact geometry of generated parts, both in original and flattened states. This process produced a single k-factor required as input for the computational model, resulting in bending radiuses for the different materials and thicknesses used in the prototype. Throughout the development, fabrication, and assembly stages of the project, a single computational model was central to a purposely built workflow enabling design control and information input and output. Input parameters included material resources and the found k-factor to enable the appropriate fillets and surface offsets wherever bending was occurring. The computational model enabled control of the overall shape, its porosity, transparency, and pattern formation. In parallel, it handled the optimization in the areas of constructibility and material resources by planarizing the components and maintaining that enough material was available for realizing the project. Finally, the algorithm was capable of exporting 3D fabrication files in step format for verification by the fabricator and handled complex tagging, unrolling, and nesting tasks. The prototype surface was articulated by computing a staggering pattern alternating between each row of components. Control over the base geometry during the development process enabled a design feedback loop, constantly informing the output. As such, clashes between the components and structural constraints for self-stability that suggested changes in the orientation of the components as to transfer forces along the vertical direction could be addressed quite late in the process. The staggering pattern facilitated the assembly of the structure by enabling simple slotted joints between each row of components. However, the above process resulted in components with non-planar elements due to the warping of the doubly curved surface. For addressing the issue, a planarization algorithm was implemented in the computational model. Finally, the availability of both galvanized and mild steel as raw material resulted in two visually distinct types of components. This property of the structure was further enhanced and turned into a design opportunity with which students experimented to produce an ornamental pattern with most mild steel components at the base, creating a random transitioning effect towards galvanized components at the top. While the research presented derives from an educational perspective, further analysis and possible applications could focus on the construction domain. As such, the areas of leftover material registration, expanding in both hardware and computational explorations, and further enhancing the structural integrity of the material through comprehensive control of the bend creases could be explored. Concluding, I would like to take this opportunity to thank the faculty, teaching assistants, and students that participated in the research project and the institutions that have supported it. Thank you very much for your attention.